Hello, I welcome you all to your own channel MSK Learnium. In this video, we will derive the equation for temperature function and Ceph function for one-dimensional heat conduction element. Right? So for that, we have to consider one bar element of one-dimensional. Let's say this is the bar element of having node 2, such that it's having 2 degrees of freedom. At each node, this is node 1 and this is the node 2, right? So the temperature at node 1 is T1 and the temperature at node 2 is T2, and the length of the element, that bar element, is having length is L, right? Now what we need to do, that we have to derive the relation for Ceph function and temperature distribution, right? Now, so for that we can say that consider a bar element with node 1 and 2 and temperature T1 and T2. So here consider a bar element with node 1 and node 2, the temperature T1 and T2, right? So now we have to consider one polynomial equation of temperature distribution. Let's say the temperature is distributed in this manner: T is equal to A0 plus A1x, right? So this is the equation 1, right? So where A0 and A1 are the global coordinate, A0 and A1 are global coordinate, okay, global coordinate. So first of all, we have to impose the boundary condition, that once come back to this bar element which we have considered. At this node 1, T1 is equal to T, right, and x is equal to, that position is equal to 0. At this node 2, that T2 is equal to T and x is equal to L, right? So these are the two boundary conditions we consider now. So we can write that boundary condition. What are the boundary condition we have? Just now we see the boundary condition. That first boundary condition is at T is equal to T1, x is equal to 0. Second boundary condition is at T is equal to T2, x is equal to L. Okay, now so substitute these two boundary condition in the above equation. We'll get again two equations. So when you substitute the first boundary condition into this equation 1, the equation will become like this, that is T1 means T is equal to T1, right? A0 is equal to A0 only, and at T is equal to T1, x is equal to 0. So when you put x is equal to 0, this term will be 0. So it means that T1 is equal to A0. Let's say this is the equation 2. Come back to the second boundary condition. T is equal to T2, right? A0 is equal to A0 only, and A1, x is equal to L. So the next equation will get, that is T2 is equal to A0 plus A1 L. So this is the equation 3, right? Now, so these equation 2 and 3, from this equation 2 and 3, you can form it into matrix form. That is, this is the T1 and T2 is equal to what? That here you have a 1, right? Its coefficient is 1. Here we don't have anything, so 0. In second equation, that is T2, its coefficient is 1 and its coefficient is L, right? And here you have this coordinate, that is A0 and A1. Alright, now we can write A0 and A1 is equal to like this, that is A0 A1 is equal to what? When this will come to this side, it will become inverse, right? So it is 1 0 1 L of inverse, right, into T1 and T2. Alright, so this is how we got the A naught and A1. Now we need to do that for further simplification. So this will be like this. So you got the value that A0 A1 is equal to 1 0 1 L inverse of T1 and T2. So its simplification will get that A0 A1 is equal to, that is 1 by L minus 0, right, into L 0 minus 1 1. Alright, inverse of that T1 and T2. So this is what you have, a A0 A1 is equal to, it is 1 by L minus 0 is 1 by L into L 0 minus 1 1, and this is what we have, a T1 and T2, right? Now actually if you look at the equation 1, right, so equation 1 is what which we have considered. The equation 1 is T is equal to A0 A1 x. If we formalize this equation into matrix form, the equation will be like this. That is, it's better we can write from equation 1, from equation 1, right? So from equation 1 we can say T is equal to 1 x and its coefficient is A0 and A1. Is it or not? A0 A1 value we know this, 1 by L L0 minus 1 1 T1 T2. So this T will become like this, that is 1 x, right, and A0 A1 is equal to, we can substitute 1 by L L0 minus 1 1, and here we have a T1 T2. Okay, so now this T is equal to 1x 1x, right, sorry, that is, yes, again we can write 1 by L L 0 minus 1 1 T1 and T2. Now what we need to do, this and this will be simplified. So this row and this column, this row, this column. So we can say T is equal to 1 into L, that is 1 by L first will get out, right? So it will be like this, 1 into L is L, x into minus 1 minus x, right? This is again 1 into 0 0, and x into 1 is x. So this is your simplification when you simplify this and this, right? So next you have a T1 and T2. Now we can say T is equal to, this L will multiply with the both, that is L minus x by L, and it is x by L, right? And this is what we have, a T1 T2, right? So further we can say this equation will be like this, that is L minus x by L is n1 and x by L is n2. So T is equal to, we can say n1 n2, and here we have a T1 T2, right? So this temperature function we have, a T is equal to n1 T1 plus n2 T2, right? So this is how we will generate the relation for temperature function in terms of the Ceph function, where n1 and n2 are the Ceph function. So you can say n1 and n2 are Ceph function, right, are Ceph function, where n1 is what, n1 is equal to L minus x by L, and n2 is equal to x by L. Alright, so this is how we will derive the relation for temperature function and Ceph function in terms of the heat conduction equation. Thank you.